Hey students, good morning. So today we are going to discuss the topic on Jordan canonical form of a matrix, definition, properties and problems. So I am Dr. K.M.Manikanadan, Assistant Professor and Head Department of Mathematics, Dr. SNS Rajalakshmi College of Arts and Science. Now first we give the definition of a Jordan block of a matrix. A matrix is said to be Jordan block if at principal diagonal all the entries are equal and the next diagonal, or we call it a super diagonal, all the entries are equal to 1. Now, we are going to see the first Jordan block of order 1. Order 1 means a matrix having only one row and one column. Here, 5 is the only diagonal element. Instead of 5, any number can come. So, this is the Jordan block of order 1. Next, we see the Jordan block of order 2. In the matrix, all the diagonal entries are equivalent to 5 equal and the above diagonal elements are equal to 1. So 5105 is the Jordan block of order 2. Similarly, we have written the Jordan block of order 3. In the diagonal entries are equal to 5 and the elements above the diagonal entries are equal to 1 1. So therefore, we have written the Jordan block of order 3. And similarly for Jordan block of order 4, all the entries in the diagonals are equivalent to 5 and the entries above the diagonal elements are equivalent to 1, which are called super diagonal elements. So therefore, this is the basic definition of a Jordan block. Next, we give the definition for the Jordan canonical form of a matrix. Let T be a linear transformation defined from a vector space V to another vector space V and whose characteristic polynomial and minimal polynomial respectively are chi a of x is equal to x minus lambda 1 power n1, x minus lambda 2 power n2, x minus lambda 3 power n3, etc. x minus lambda r power nr. Here lambda 1, lambda 2, lambda 3, etc. lambda r are the eigenvalues of the characteristic matrix chi a. Similarly, here MA of x represents the minimal polynomial denoted by x minus lambda 1 power m1, x minus lambda 2 power m2, etc. x minus lambda r power mr. Here m1, m2, m3, mr are called the indices of the minimal polynomial MA of x, and n1, n2, n3, nr are called the indices of the characteristic polynomial chi a of x. And one more thing, the sum of the indices n1 plus n2 plus n3 plus plus etc. plus nr equal to the order of the matrix, where here lambda i's are the distinct scalars. Now then, T has a block diagonal matrix. This diagonal matrix is called the Jordan canonical form and it is denoted by lambda I 1 dot 0, lambda I next one below elements is lambda I 0 0 0, the second row 1 lambda I 0 0 0, and the last row 0 0 0, column you see last column 0 etc. dot. Last entry will be lambda I. Now the Jordan corresponding to Jordan canonical form will have Jordan block. So the Jordan block will have the following properties. The Jordan block is denoted by Jij. Here Jordan block is formed for ith row and jth column. So there is at least one Jordan block Jij of order Mi, and all the other Jordan blocks are of order less than Mi, which are corresponding to the eigenvalue lambda I. So corresponding to each value lambda I, there is at least one Jordan block of order M. Similarly for everyone. See here, in the MA of x, the eigenvalue is lambda 1 and whose power is m1. So which shows that there is one eigenvalue, there is one Jordan block of order m1 with respect to for the eigenvalue lambda 1. Similarly, for x minus lambda 2 power m2, from this we get that there is at least one Jordan block of order m2 with respect to the eigenvalue lambda 2, etc. Now the number of Jij's of each possible order is uniquely determined by A, and also the number of Jordan blocks equivalent to geometric multiplicity of the corresponding eigenvalue lambda I. These are all the four properties of the Jordan block. Now, next we discuss one problem. Reduce the matrix A to the Jordan canonical form whose characteristic polynomial chi A of t and minimal polynomial ma of t are given by chi A of t equal to t minus pi the whole power 4 into t minus 7 the whole cube. Here eigenvalues lambda equal to 5 and lambda equal to 7, and the orders are 4 and 3. So therefore you add 4 and 3, you will get 4 plus 3 equal to 7, which is the order of the required matrix. And in the minimal polynomial MA of t, we are having eigenvalues lambda 1 equal to 5, lambda 2 equal to 7, and the order its indices m equal to 2. So therefore m equal to 2 shows that corresponding to eigenvalue 5, there is one Jordan block of order 2. Similarly, corresponding to the eigenvalue lambda equal to 7, there is one Jordan block of order 2. The remaining Jordan blocks are of order less than 2. Now, by keeping all these in mind, so now we have constructed the Jordan canonical forms. As I already said, the order of the matrix n1 plus n2 equal to 4 plus 3 equal to 7. Index m equal to index of the minimal polynomial 2. By property, there is at least one Jordan block of order m equal to 2 for the eigenvalues lambda equal to 5 and lambda equal to 7. And the remaining Jordan blocks are of less than order 2. Now there are two possible Jordan canonical forms of a matrix. First one is 5105, which corresponds to eigenvalue lambda equal to 5, which taken from the MA of t, and go to chi A of t, characteristic t. In that you will get t minus pi the whole power 4. So for already eigenvalue 5, we have framed one Jordan block. In chi A of t for 5, you can form another Jordan block of order 2. That is 4 minus 2. You subtract the index value 4 with corresponding to lambda equal to 5. You take here also corresponding value lambda equal to 5, 4 minus 2, 2. So you frame another Jordan block of order 2 with respect to the eigenvalue lambda equal to 5. And the order of the matrix should be here 7. So now by our definition, so there must be one Jordan block of order 2, at least one Jordan block of order 2 corresponding to the eigenvalue lambda equal to 7. So therefore 510 in the first form, see here, it is marked in red column 5105. Next block 5105. Next block is designed for eigenvalue lambda equal to 7 of order 2, 7107. The remaining block should be a single block of order 1 which corresponds to the eigenvalue lambda equal to 7 because a single block. Because in chi a of t, the eigenvalue 7, the power may be up to go up to 3. So already for 7 we have given 2 in ma of t and for 1 in chi a of t. And next possible chance, there is at least one Jordan block of order 2 for lambda equal to 5 and lambda equal to 7. See in the second Jordan canonical form, we have constructed 5105 for the eigenvalue 5 corresponding to the eigenvalue 5, we have constructed one Jordan block, and the in chi a of t, the power of 5 is almost to 4. So therefore, you subtract 4 minus 2, you will get 2. But there must be a single block corresponding to the eigenvalue lambda equal to 5. So therefore, we have constructed two single blocks corresponding to the eigenvalue 5. And next in the characteristic polynomial 7, for the eigenvalue 7, there is one index is left. So therefore, we have framed one single block for the eigenvalue 7. The remaining entries are equal to 0. Next, we find the canonical form of a next problem matrix. So A equal to 3, 2, minus 3, minus 1, 2, 1, 0, 1, 1. So to find, first we find the characteristic polynomial using the formula determinant A minus xi equal to 0. I use the unitary matrix. You form the substitute the values of A minus x into I 1, 0, 0, 0, 1, 0, 0, 0, 1. Solving this equation, you will get equation x cube minus 6x square plus 12x minus 8. This is the equation 1. Now, randomly by substituting x equal to 2 in the equation, it is satisfied. Therefore, x equal to 2 is 1 root, and therefore x minus 2 is a factor. The remaining factors are obtained by applying the synthetic division method. You will get x minus 2 whole square is another factor. Therefore, characteristic equation chi a of x is equal to x minus 2 whole cube. Now, the possible minimal polynomials are x minus 2 whole square, x minus 2 whole cube. Now, we find by applying the Cayley-Hamiltonian theorem. So, we verify the and we verify the characteristic polynomial, we verify the Cayley-Hamilton theorem a minus 2. For x minus 2, you instead of x, you put a minus 2i. The matrix value is not equal to 0. Therefore, x minus 2 is not a minimal polynomial. And we next check it for a minus 2i the whole square. which is also not equal to 0. Therefore x minus 2 whole square is not a minimal polynomial. Then we check it for a minus 2i the whole cube, which is equivalent to 0. It satisfies the Cayley-Hamilton theorem. So therefore x minus 2 whole cube is a minimal polynomial, and ma of x is equal to x minus 2 the whole cube. So by property, there is at least one Jordan block of order 3. Here m equal to 3. The corresponding to the eigenvalue lambda equal to 2. So here eigenvalues are both are same, and the order of the matrix is also equal to 3. So therefore there is only one Jordan block of order 3. So we have constructed one Jordan block of order 3. The diagonal entries are 2, 2, 2, and above the diagonal entries are 1, 1. Remaining elements are 0. We have formed the one Jordan canonical form for the given matrix. So dear friends, I hope that you understand the Jordan block concept well. Thank you.